Hello viewers, welcome back to the course. So today we are going to start with the lecture 14. So in the previous lecture we have discussed about the Newton-Raphson method and about its convergence. So in this lecture we will discuss further that what will happen when we have multiple roots. So in that case, like for example, I have an equation like x minus 3 whole square equal to 0. So in this case my function f(x) is x minus cube whole square. So it has the roots x is equal to 3 and 3. So in this case we can say that this equation f(x) equal to 0 has two roots, and that is 3 3, but the roots are repeating and its multiplicity is 2. So what will happen that suppose I want to find the root of such type of equation using my Newton-Raphson method, because if you see here, if I take the f dash x, so f dash x will be 2 x minus 3. So in this case my f3 is 0, and from here I can see that f dash 3 is also 0. So what is happening here? This is also 0 and this is also 0. So we have a Newton-Raphson method for multiple roots. So how it works? So the method is same. We have a equation f(x) equal to 0, and suppose the equation, suppose f(x) equal to 0 has multiple root, and that is we take it alpha. So it means that f of alpha is 0 and f dash alpha is also 0. So in this case my Newton-Raphson method, I know that my Newton-Raphson method is xn plus 1 is equal to xn minus the function value of the function at xn and derivative at xn, where n is starting from 0, 1, 2, 3 and so on. So in this case, and we also know that it is of second order, the rate of convergence, second order rate of convergence. So what we do, just to deal with the multiple roots, we have the same equation, but we multiply by some m here, and then we write xn and f dash xn. So that is my equation. Now, and I also know that my root alpha can be written as xn plus en. It means en is the error at the nth step, and from here I know that my xn can be written as alpha minus en. So just if I want to apply this method, now I want to see that what will be the rate of convergence. So let us call it 1, equation number 2, not 1, this can be taken as 2. Now the same way we have done for the Newton-Raphson, from here I can write this as a alpha minus En plus 1, and that is alpha minus En minus m f alpha minus En divided by f dash alpha minus En, and from here I can cancel my alpha, and then from I can write En plus 1 is equal to, so minus sign is here, minus sign is here, so I can write this as a En f dash alpha minus En plus m times f alpha minus En divided by f dash alpha minus En. Now from here, because in the same way we can do that, my function is differentiable, so I can apply my Taylor's expansion. So, from here this equation becomes the f dash alpha minus E n f double dash alpha plus E n square by 2 factorial f triple dash alpha and so on, plus m times f alpha minus E n f dash alpha plus E n square by 2 factorial f double dash alpha and so on, and divided by my f dash alpha minus E n f double dash alpha plus E n square by 2 factorial f triple dash alpha, so on. So, this way we can define my Taylor expansion. So, from here I can write my E n plus 1 is equal to, now I have the terms. So, I know that my f of alpha is 0. So, this alpha, suppose the alpha is the root of the equation and I do not know about its multiplicity, that whether the root is multiple or not. So, in that case I know that my f alpha is 0. Now, I can collect the terms corresponding to f dash alpha. So, if I collect the term corresponding to f dash alpha, I will get my E n from here and minus m times E n. So, this one I have collected and this is equal to 0. Then I can write my f double dash alpha. So, if you see from here, it will be minus E n square, and from here this will be plus m E n square by 2 factorial. So, that is equal to 2. So, that is f double dash alpha, plus I can collect the terms corresponding to f triple dash alpha. So, f triple dash alpha will be from here, you can see that this one can be written as E n cube by 2 factorial, and the next term will be m E n cube by 3 factorial, and that will be divided by. So, from here I can write my f dash alpha minus E n f double dash alpha plus E n square by 2 factorial f triple dash alpha. So, this is the same denominator I can write. Now, from here if you verify, just simplify this one. So, from here I can write my E n, I can take common. So, that will be m minus 1 f dash alpha. Then from here I can take my E n square common. So, if I take E n square common, I will get my m by 2 minus 1 f dash alpha, plus from here I can collect my terms E n cube. So, inside it will be m by 6, even I can take the 2 common. So, this one I can write as 3 minus 1 f triple dash alpha. And from here my f dash alpha minus E n f double dash alpha this one. Now, from here you can see that everything depends upon that what is the value of m. So, in this case I will just take the common value of f dash alpha from here and f dash alpha from here, and then you can see that this will be. So, now everything depends upon that what is the value of m. Now, if m is not equal to 2, so in this case what will happen? So, if this is an m is not equal to 2, then from here I can write from here E n plus 1 will become. So, f dash alpha I can take common from here. So, it will be I can write this one. So, m is not equal to 2. So, it will be minus E n m minus 1 f dash alpha, and from here also I can take this f dash alpha common, and then inside it will get f double dash by f dash plus E n square f triple dash by f dash and so on. And from here, so f dash alpha I can take from here common, and inside I will get this value, then I will get E n square m by 2 minus 1 f double by f dash and so on. So, from here you can see that this will cancel out. If I take this one as at the numerator and apply the binomial expansion, the same one we have done. So, in that case you will see that my E n plus 1 will be, if I cancel out this one and ignoring the higher power of E n, then this terms will be minus m minus 1 E n, if I ignore the second order powers of E n. So, in this case, if you will see that this method becomes of first order. So, when m is not equal to 2, the method will be of the first order. Now, what will happen if I have m is equal to 2? M is equal to 2 means the root alpha has multiplicity that is equal to 2. It means my root f alpha is 0 and f dash alpha is 0. So, in that case what will happen? So, in that case I can take this term 0 and this term 0. So, my E n plus 1 can be written as, so in that case my this will be 0, term this will be 0. So, I will get only E n square. So, m will be 2. So, this will also vanish. So, this term will vanish, this term will vanish. I will get only this term E n cube by 2, and my m is 2. So, it will be 2 by 3. So, minus 1 by 3 and f triple dash alpha and all the other terms divided by. So, this will cancel. So, from here I can take my E n f double dash alpha, I can take common, maybe I can take minus with a minus sign, and then from here I can write 1 minus. So, E n will be common. So, it is E n by 2 factorial f triple dash by f double dash and so on. So, from here now I can take this as the numerator and I can apply my binomial expansion. So, from here if I take this one, then I can cancel out by this term. So, from here and minus sign will go. So, from here I can write that I will get by f double dash alpha and then 1 by 6, because this minus and this minus sign, and E n square. And maybe I can take this one and then just ignoring the higher power of E n more than cube. So, from here you can see that my least power will be E n square, and from here I can write that this is equal to k E n square. So, now, so this one can be written as in this form, where my k is equal to 1 by 6 f triple dash alpha by f double dash alpha. And so, it means that just to keep the Newton-Raphson method of the second order, I put m is equal to 0, and in that case I am getting the second order convergence. So, rate of convergence is 2. So, based on this one I can say that in the future I can apply my Newton-Raphson method Newton-Raphson method always in the form of xn plus 1, xn minus m, f at xn and f dash xn. Because when it has the multiplicity only 1, then I will put m is equal to 1, and in that case it will be the Newton-Raphson method to find out the simple root, and otherwise I will put the multiplicity here and then I will put these methods to find the multiple root. So, this is all about that how we can apply the Newton-Raphson method for multiple root. Now, we will go further, and then suppose we have a system of equation, like suppose I have a f x y equal to 0 and I have g x y equal to 0. For example, I have equation cos x minus x e x equal to 0 minus x e raised to power y equal to 0, and in another equation I have x into sin y equal to 0. So, in this case suppose I have two equations and then I want to find the roots of this equation. So, f x y equal to 0 and g x y equal to 0. So, that is we call it simultaneous equation. So, how to find out the roots of this simultaneous equation? So, let alpha and beta, these are the roots, is a root of the system. So, I have the system. So, in that case this is equal to 0 and g alpha that is equal to 0. So, this is the value of the equation, value of the system at alpha beta, and where alpha beta is the root of the system. Then, so how we can apply the Newton-Raphson? So, I want to apply Newton-Raphson method for system of equation. So, in this case what we will do, let, so from here I can write that let alpha is x naught plus some h. It means that x naught is my initial guess plus some error, and I will get my solution, that is alpha, or I can say beta is equal to some y0 plus k. So, this is what I am considering, because if we know that in the iterative methods, if I put x naught plus h1, then I will get x1, then I will put x1 plus h2, then I get x2, then if I put x2 plus h3, then I get x3, and so on. So, what I am doing, that I am considering all these h1, h2, h3, and maybe I am taking the maximum of this error or the summation of this error, and I am considering that I get my alpha x naught plus h. So, I am making this parameter, this error, as independent of the iteration. So, that is why I am considering this x naught plus h. Similarly, I am considering beta is equal to y naught plus k. Now, from here I know that alpha beta is equal to 0, because this is the root. So, from here I can write f of x naught plus h and y naught plus k. So, that is equal to 0. Now, this function is a well defined function, its partial derivative exists. So, I can apply my Taylor expansion for several values, for I can say for two variables, that is x and y. So, how will we can do that? So, in this case, so this is equal to 0 f x naught plus h and y naught plus k. So, I am considering, I am expanding this Taylor expansion about the initial guess, that is x naught and the y naught. So, this I know that can be written as x naught y naught plus h del f by del x plus k del f by del y at the point x naught y naught plus 1 by 2 factorial h square del square f by del x square plus 2hk del square f by del x del y, this is the mixed derivative, partial derivative, plus k square del square f by del y square, and this is value at x naught and y naught, plus the higher terms. So, this one I can consider. Similarly, I can apply my 0 to the another function. So, from here I can write this as g x naught y naught plus h. I can write like a gx. So, that is same as del g by del x plus k g y. So, this is at x naught y naught plus 1 by 2 factorial. So, I can write h square gxx plus 2hk gxy plus k square gyy at x naught y naught and the higher term. Now, from here I can find out that, so I get these two equations. Now, what I do, I now neglecting the second and higher order, terms of h and k, that is all the terms h square, k square, h k and higher. So, I am ignoring that one. So, based on this one I will get only this equation. So, this will become 0 is equal to f x naught y naught plus h f x plus k f y at x naught y naught. So, I get only this term. Similarly, I will get 0 is equal to g x naught y naught, and that is plus h g x plus k g y at x naught y naught, and all other terms we can ignore. So, from here I can write this as h f x at x naught y naught plus k f y k f y at x naught y naught, and this is the value of the function at the initial guess. So, I can take this as on the right hand side. Similarly, I can define the terms from the second equation g x. I am taking the value at this k g y at value x naught y naught, this one. So, if you see that this become a system of equation, and from here I can write this equation as f of x, f of y, g of x, g of y. So, this is the matrix I am getting, and then I can find h k, and on the right hand side I will get minus of f and minus of g at x naught y naught. So, this is a system equation, and I am getting this system equation at the initial guess, that is x naught y naught. This is also about the x naught y naught. So, based on this one I can solve this equation, the system equation, using the Cramer's rule, because I am considering that this matrix is non-singular, because my function f x and f y and g x and g y, that give me the non-singular matrix. So, based on this I can find my h. So, that h will be minus f minus g f y g y divided by so from here I can write that this determinant will be minus f g y minus plus f y g divided by f x g y minus g x f y. So, from here I can write minus of the sign. So, I can write f g y minus g f y divided by f x g y minus g x f y. So, that is my h we can find. Similarly, we can find the value of k using the Cramer's rule. So, I will get my k is equal to f x g x minus f and minus g divided by the same. So, this is my f x g y minus g x and f y. So, based on this one I can write. So, from here I can write minus g f x plus f g x divided by the same factor, and this is the minus sign I can take common. So, this will be g f x minus f g x. Here it was f g y minus g f y, here it is with respect to x, and then f x g y minus g x f y. So, that is my another. So, based on this one, now I can find my h and k from here. Now, as I told you that what is going to happen in the real way, that we start with the x naught, and then suppose based on the x naught I will get the value of this h, and I will get y naught, and this is the value of the k I am getting. So, after doing all this calculation I am able to find only this value, x naught that is already known to me, h I can find from here, y naught is already known to me, and k is from here. So, that will be give me, I will treat this as a my approximation, that is my x1 and y1. Then the same way I will do from here, I will find out my x2, that will be x1 plus then h I will find out, and y2 will be y1 plus k. So, this way we can have a iterative methods for finding the root using the help of h and k. So, from here I can write that my xn plus 1 will become xn, that is given to me, plus hn, and yn plus 1 is equal to yn plus kn. So, based on this one I can improve my value of the root with the help of this, and that is the methods. So, with the iterative methods I am able to find the roots for the system of linear equation. System of linear or non-linear equation does not matter, but we have a system of equation and we can find the roots using the Newton-Raphson method. Now, based on this one, so this is all about that how to find the root of the system of equation. So, based on the Newton-Raphson methods, now we are able to find that what will be the rate of convergence when we have a multiplicity more than 1 for a root, and then we have extended this that how suppose we have a system of non-linear equation and we want to find the roots. So, based on the Newton-Raphson method and by this expression we are able to find the root of the system of equation. So, maybe in the next lecture we will go further from this. So, thanks for viewing, thanks very much.